In our previous video, we outlined some basic graph theory and terminology. We also discussed how we can store a graph using either an adjacency matrix or an adjacency list. This video will explain graph traversal, the process of walking along the nodes of a graph in order to solve a problem. There are two common ways to traverse a graph: depth-first search, abbreviated by DFS, and breadth-first search, abbreviated by BFS. Our goal is to eventually be able to visit every node contained in the current connected component of the graph. Let's go over how they work. DFS begins at a starting node. All nodes that are connected by an edge to the node we are currently on are neighbors. DFS begins by randomly choosing a neighbor of the starting node and traveling along the corresponding edge to that neighbor. Then, that neighbor becomes the new starting node. We then randomly choose another neighbor to go to from our new starting position. It is important that we do not choose a neighbor that has already been visited, as represented by the green dots in the graph. We repeat this process over and over. If, at any point, there are no more unvisited neighbors adjacent to our current position, DFS returns to the last visited node, which has an unvisited neighbor, and the algorithm continues from there. Eventually, all the nodes in the connected component will be explored, and the algorithm will end. This is where the name depth-first search comes from. The algorithm searches deep into the branches of the graph, only returning to unexplored neighbors when it reaches a dead end. BFS takes a different approach. Instead of exploring each unvisited neighbor one at a time, it visits all of the unvisited neighbors at once. First, it randomly visits neighbors of the starting node until all the neighbors have been visited. Then, it repeats this process for each of those visited neighbors. In other words, the algorithm first visits all nodes one edge away from the start, and then visits all nodes two edges away from the start, all the way until there are no more nodes to explore. Since this algorithm explores all pathways at once, it doesn't immediately go very deep into the graph, hence the name breadth-first search. DFS and BFS can be used to solve different problems. For example, BFS can be used to compute the shortest distance between the start node and any other node in the connected component of an unweighted graph. Since the algorithm visits all nodes with incrementally increasing distances, it is guaranteed that it will find the shortest distance upon reaching the target node. Now that we've gone over how DFS and BFS work, let's try applying them to the third question of the USICO 2016 December Silver Division Contest, Moocast. If you would like trying the problem on your own first, make sure to pause the video. Here's what the problem asks. Farmer John's N cows want to organize an emergency Moocast system for broadcasting important messages among themselves. Instead of mooing at each other over long distances, the cows decide to equip themselves with walkie-talkies, one for each cow. These walkie-talkies each have a limited transmission radius. A walkie-talkie of power P can only transmit to the other cows up to a distance of P away. Note that a cow A might be able to transmit back to cow B even if cow B cannot transmit back, due to cow A's power being larger than that of cow B. Fortunately, cows can relay messages to one another along a path consisting of several hops, so it is not necessary for every cow to be able to transmit directly to every other cow. Due to the asymmetrical nature of the walkie-talkie transmission, broadcasts from some cows may be more effective than from other cows in their ability to reach large numbers of recipients, taking relaying into account. Please help the cows determine the maximum number of cows that can be reached by a broadcast originating from a single cow. Here's a rough walkthrough of a possible solution. The graph we will use has cows as nodes. If a certain cow A is able to directly transmit a message to cow B, then we will connect A to B with an edge in the graph. We can store this graph in an adjacency list. We can then iterate through all possible pairs of cows using two nested for loops. Since n is less than or equal to 200, the time complexity of big O of n squared shouldn't be a problem. For each pair of distinct order cows, we can use the distance formula to check if the distance between them is less than p sub I. If it is, we can add the edge from cow A to cow B on our adjacency list. For example, suppose that cow 1 is at the coordinates x equals 0 and y equals 0 with power 6, and cow 2 is at the coordinates x equals 3, y equals 4 with power 3. The distance between the cows is 5, and since 5 is less than 6, cow 1 is able to transmit messages to cow 2. However, the reverse is not true. Therefore, we can only add an edge from cow 1 to cow 2 on our graph. We wish to find the starting cow that will be able to transmit a message the furthest in this directed web of cows. So, we apply DFS to every possible starting cow, keeping track of the number of nodes visited with each search. Then, we simply select the highest node count and output that as our answer. Note that this is a directed graph, since as pointed out in the problem, two cows may not be able to communicate mutually. Hence, it is necessary to use DFS on every cow since different start nodes yield different answers. DFS has a time complexity of big O of n, and we'll have to apply their algorithm n times, yielding a total time complexity of big O of n squared. Again, this is well within the time limit. Of course, actually implementing DFS and BFS in code is a tad bit more complicated than this. To learn more, check out our other articles and videos on our website. Also, don't forget to like, comment, and subscribe.